Hello everyone, good afternoon. I'm just getting up my screen. Hope everyone is doing well. It feels weird because it's been a long gap, right, with the spring break. Let me just make sure that I have my PowerPoint kind of ready over here because we're going to be using part of the PowerPoint. So if I want to share the screen, I think I can share the screen. I just want to go through the presentation very fast. Good. So yeah, I'm going to be using the PowerPoint as well as my the board work. So I'm just trying to make sure that I'm in line with you guys. Okay, sounds good. I think we're good. And the PowerPoint should work out to share with you guys. Okay, how is everyone doing? Let's maybe we can have a little chit chat for a few minutes. How are you guys doing? Hi, Devon. Hi, Andres, Eshan, Kauli, Juliana, Isaac, Adil, Sebastian, Ray, Jaslyn, Elana, Matthew, Saeed, Roxana, Alexia, Benita, Varun, and Michael Coppins. How is everyone doing? Did anyone have some fun in the spring break?
I had a question about the exam.
Oh, we have a question about the exam. All right, Sebastian. Yeah, what's your
Did
question?
you receive my emails?
I received a lot of emails. I received a lot of emails about technical problems. I'm not sure how technical are the technical problems. I have deliberately not looked into it. I have decided to wait until tomorrow to address them. So I haven't read any of the emails. Whatever happened, happened. I even got one email, one phone call in my office that seemed very sincere and very, traumatic. Somebody's computer was acting weird. I received all of the emails. I'm going to address them tomorrow, starting from tomorrow. I was out of town during my spring break toward the end. I was also not well for the last 2 days because of the second vaccine. So I'm kind of recovering. So I'm going to start reading them. I've decided that I'm not going to read them today. I'm going to read them tomorrow and go from there. Anything, Arjun?
Okay.
We can, yeah. So let me read the emails and then we will go from there. As I mentioned that if somebody had trouble submitting it on time, and if somebody must um, submit the exam as an attachment to my email, there will be a point deduction, there will be a penalty. And I'm going to stick to it this time. I'm not going to let my empathy overpower my I'm not going to listen to my heart this time. I'm going to listen to my brain for a change. I usually let go of things, but this time I'm not. Okay, so there'll be a point. There'll be a deduction of points, unless I'm absolutely convinced that there was a problem. Yeah. Anybody else?
I just have a question because I was trying to submit at, like exactly at 4:45 because usually when you submit assignments like it says 11:59 you can still submit at 11:59, but for some reason at 4:45 you couldn't submit
That's
on
too bad.
Canvas.
Well, then you should have kept yourself some time. I had mentioned that. Yeah. So that's what happens. Life is tough and unfair. So if you try to submit at 4:45 and you couldn't submit at 4:45, then well, we live and learn our lessons, right? So there will be some fun.
But I emailed you at that same time. Would that's still a point deduction then?
Yes. Well,
Okay,
I'll figure it out. I mean, when did you email it to me? At what time?
exactly 4:45. 'Cause,
I'll use some judgment.
how big is the points deduction?
10 points. Okay. Yeah. I just don't want the same history to repeat in the final. I'm not really happy about it. I mean, most people don't have trouble submitting it on time. And you guys have your cell phone, and you can have your hotspot. You know how to do that. I mean, you guys know it better than I do, how to deal with the technology. And I kind of refuse to believe that most of you had trouble. I mean, there was a very genuine and sincere a phone call in my office while I was here, and I know that that was a very legitimate reason. And I can tell the difference between legitimate and illegitimate reason. So yeah, there will be some penalties so that next time in the final and the quiz, you guys don't wait until the last minute. You guys need to finish it on time, and yeah, you just don't have the luxury to work on it for 1 hour and 15 minutes. I have talked to some of you guys, and some of you guys have told me that the exam could have been done in 45 minutes or half an hour if you knew your material. So I'm not going to cut any slack this time. There will be some penalty so that this doesn't happen in the final. All right, I'm probably not bearing really great news after the spring break. Some my sincere apology, but then sometimes you have to be a little tough. Okay, you guys are getting out of the pandemic with 128B, and I think yeah. So these are learning lessons. We have said the same thing to our son. Like sometimes you get a B, and you fall on your face and you get up and go and learn your mistakes. He has done something very similar, like waiting until the last thing, 11:59 seconds to turn in his homework, and just didn't work out. And he would refuse to reach out to his instructors or cutting some slack. And, well, he doesn't do it anymore. So this is all learning lessons in life. I'm not saying that I need to be your philosophical guru or pandit or your advisor. I'm not trying to take that role, but then sometimes life is tough. So anything else? I will still use my best judgment to just kind of like see how things are. I don't think if you are genuinely having a problem, you will be suffering. Your grade is going to go down a notch. I don't think that's going to happen. I will make sure that that doesn't happen. Okay, but as I said, so when I trust someone, I expect the person to reciprocate. I'm not saying anybody has failed to reciprocate. I do not know. I'm still going there and see how things are. So, but I think your values and morality and sense of ethics is also important. Again, this is not a religious class to make you a better human being that way. But I think you should think about it sometimes. Just sticking on the right path is sometimes important. All right, with that uncomfortable discussion, let's move to the board and let's talk about NMR spectroscopy. Any other last minute questions? Thanks for keeping your cameras on. This is the class that keeps, I see maximum number of faces. Devon, Andres, Eshan, Gauli, Juliana, Isaac, Adil, Bastian, Hannah. Thank you for keeping your cameras on. Varun too, in front of the red, beautiful bridge. Hi, Varun. Did anyone go anywhere outside Fresno? I mean, what's wrong with you people? Why don't you just take your car and go somewhere?
I live in Elk Grove, and then I live in S Valley down here near Fresno. So it's kind of near Dunlap. So I kind of swap places.
There is a pharmacy school in Elk Grove. You know that, right? North.
Yeah, actually, it's birthday weekend for all my family. So I had my birthday over spring break, and then my sister had hers the day after mine, and then I think yesterday was my sister's
Okay,
birthday.
where is our cake? Hannah?
No, the cake only, well, because I'm an oldest of 11, so the cake only lasts one sitting.
One of my ex-students, she's in dental school right now. She had a half gallon of milk. This is a very distracted. It has nothing to do with NMR spectroscopy. She had some milk like bought, and somebody bought it for her, and then it was extra. So I said, she said, what do you think I should do with it? I said, just gently boil it with some little bit of sugar, and since it's filled with fat, it's going to turn into some kind of dessert. And she sent me a picture. Oh man, that was just so yummy. I actually haven't had lunch yet, so I'm just thinking about food for the last half an hour, 1 hour. So let's
It's
not
kind of
let's not
of
talk
yogurt.
about food at all. Okay, we'll be torturing you. Anything else? Did anyone else travel anywhere or have any fun? Someone in my 128A said that went for fishing, and did a lot of fishing. Apparently, this guy never played video games, but he would get in trouble for fishing expeditions. That sounds like a phrase, like I'm going for a fishing expedition. Anybody had any fun in spring break? Come on, somebody must have had some fun. Michael, what did you do, Michael? Did you just look at your NMR spectra? Is Michael torturing you guys during his SI sessions? Okay, nobody wants to talk. Helena, Yasmin, Alexia, Roxana. Michael is pretending that he's not kidding. Hi, Dane. Thanks for turning your camera on. Okay, let's not waste any time. Let's get started. So let's talk about NMR. I'm going to go over some basic stuff, and then I'm going to switch to the PowerPoint. Okay, let's go to the board. We are being recorded. Yeah, there was on the chat. I read a couple of novels. Somebody reads novels? That's great. I haven't read a novel for like decades. I'm like 100 times your age, but then I should read probably some books. I wouldn't worry too much about the test that we just had. If you guys getting anxious about it, I will read the emails. I'll go from there, and we'll figure it out. Okay. If you are on the right track, on the proper track, I don't think nothing is going to happen that's going to push your position and notch down. So your A is not going to become B, B is not going to become C, or C is not going to become D. So don't worry about that. So if you're doing everything the right way, you'll be fine. Okay. All right. So 128B. Today is 4/8/21, and we're talking about NMR spectroscopy. Okay. I hope you remember, because you are supposed to study for the test, and we had some questions about NMR. So the whole deal is that the nuclear magnets, like for example, we are dealing with, let's say, some of the nucleus of certain elements behave like magnets. That's the bottom line. Okay. And for hydrogen atom, when we are looking at different hydrogens, the hydrogen nucleus, okay, which has one proton, that can behave like a magnet. So it behaves like a magnet, yeah, and they're usually random when there is no external magnetic field. Just like if the Earth's magnetic field could be turned off, and if you'd hang a bunch of bar magnets using a thread from the middle, and they would just be suspended, they will be pointing at multiple directions. So that could be pointing up and down and sideways, and who knows which direction, right? So they're all random. So then when you put an external magnetic field, which is B0, then they're all lined up. Okay. I'm going fast because this is something that we have already discussed in the past. So they all line up with the main external magnet. And then what you do is then you apply, while B0 is there, you apply in the opposite direction a radio frequency, completely in the opposite direction, just enough power to turn the magnets, like overpower the strength of B0 to push the magnets, nuclear magnets, in the opposite direction. So now they're pointed down. Okay, we have already talked about it. So now they're against B0. Then, as I said, you turn off the radio frequency. That's not exactly how it's done. So if anybody has read NMR spectroscopy like deep and wide, and you find something wrong with what I'm just saying, just forgive me. I don't want to get there at this point, okay? So turn off their external magnetic field, and then the magnets go back to their original orientation, okay? And you release energy. So that energy release, this is the happy state, okay? This is low energy. Low energy, okay? Let's call it alpha. Oftentimes alpha is shown, in functional groups, you have learned that if you have CH3, CH2, CH2OH, right? For example. So oftentimes we say, this is your alpha carbon, that's your beta carbon, and that's your gamma carbon, right? So that's one way to use the Greek alphabets to designate different carbons as you're moving away from the functional group. Closest to the functional group is alpha, beta, gamma, delta, epsilon, etc., etc. Okay. Similarly, alpha and beta are also used for describing low energy and high energy. Alpha is generally low energy, beta is high energy. So this is low energy, alpha, okay? I'm just going to put the word low in parentheses, okay? So let me erase it because this is going to probably cause some confusion. This is the low energy. This is the high energy, okay? E beta, this is high, okay? And when you go back from beta state to alpha state, you release energy, okay? So delta E is E beta minus E alpha, okay? That's the energy that's released when the magnets are, the term is called relaxation. When the magnets are relaxing from the high energy to low energy, this process is often called relaxation. Where do I write it? Green is not a good idea. This is called a relaxation. And the physics involved with this process is just mind-boggling. And I'm really not well versed with it. I have studied it in the past in graduate school, but I have forgotten much of the PChem. I'm not really that gifted with PChem. Okay, that's a confession. So this is called a relaxation process. So what do we measure in the NMR spectrum? We measure delta E and we plot it. So this is what is measured. That's the key, one of the key components or key fundamental concepts of NMR spectroscopy. This is measured. Delta E is measured and plotted. Okay, that's the key. Now the next question that we have discussed briefly before spring break is well. So it's great that delta E is plotted in the NMR spectrum, but shouldn't all hydrogen atoms in proton NMR spectroscopy, in 1H NMR spectroscopy, because we are looking at hydrogen nucleus, shouldn't that be the same energy? Well, it is not. If it were the same energy, then we wouldn't be talking about it. We wouldn't have NMR spectroscopy developed. Nobody would be making GE and other companies like Bruker and other companies, Varian. They wouldn't be manufacturing NMR spectrometers and selling it to different institutions for like millions of dollars or hundreds of thousands of dollars, okay? Delta E is measured and plotted. That's bullet point number 1. Bullet point number 2 is, that's very important, delta E is different you know what? It should be written in another color. Delta E is, delta E, let's use a different word. Delta E varies for different types of the same nucleus, like hydrogen nucleus. We're talking about hydrogen, so let's stick with hydrogen. So different types of hydrogen nuclei, multiple, plural, so it's not nucleus, it's nuclei, it's EI, okay? So this is key. That second bullet point is more important than the first bullet point. Yeah, so you have a magnet, nuclear magnet, it's lined up with external magnetic field. You apply the opposite direction radio frequency and it flips. Then you turn it off, it flips back, releases energy, you measure that. That's not that big of a deal. The big deal here is that the different types of hydrogens show appreciable difference in their magnetic strengths, which can be measured and which can be plotted and which can be observed as different shifts or different signals, or they call different signals, all these absorptions, the delta E. So the delta E value for this hydrogen in a molecule versus another hydrogen in a molecule, that varies, and we can measure it and we can see it. If none of this worked, if it existed, but with our resolution available signal to noise ratio, or if with our technology, if we could not show the peaks like different peaks, then NMR spectroscopy wouldn't exist by this time. Okay, so all of this worked out, and now we started having NMR spectrometers from the middle of the 1900th century. Okay, and things dramatically changed. NMR has been a heaven-sent technology that allows us to see not only organic molecules but biochemical molecules too. Like someone like Dr. Krishnan, they do NMR spectroscopy on proteins which have hundreds of different types of hydrogens. And it's not just different types of hydrogens, they do all kinds of multiple dimensional NMR spectroscopy where they try to interact different hydrogens with each other, and it gets absolutely mind-boggling. So NMR is amazing. Okay, NMR is really, really amazing, truly amazing technique. So this is what is being plotted, and this number varies from hydrogen to hydrogen atom, and it's true with other nucleus too, like carbon-13, different carbon-13 nucleus, different carbon nuclei. They also vary with their strength. Okay, different other elements nucleus, they vary with their strength depending upon the electronic environment. What makes delta E different for different hydrogen nucleus is the electronic environment. So that's critical. The reason for this, why delta E varies? Delta E varies. Delta E is different because of the electronic environment. Because of varying electronic environment. Okay, take a look at it. This is just a quick review. So we're going to get into some more details of this NMR technology. So take a look at it and make sure that you get the picture. You have the picture behind the fundamental rules and principles of NMR spectroscopy. That's like the quick, cartoon diagram of this business. And this is what is being measured. What is delta E? You should know the delta E is high energy or minus less energy. Less energy is the energy with B0. This is against B0, and that's what is being measured. And there is going to be a little bit of equation that we're going to talk about briefly. And delta E is different for different types of hydrogens. Okay, just take a look at it for a second. 15 seconds. All right. So how is delta E? How is the strength of the magnet being affected by the electronic environment? Well, here is the nucleus. You know what? Let me just draw the nucleus as if it's a magnet. Let's say this is the nucleus. Okay. This is the hydrogen nucleus, and it is being, that's the Death Star and that's the shield. I'm talking like a maniac who is obsessed with Star Wars. Okay, that's where the electronic shell is. Okay, that's the electronic shell. So it's like a spherical shield, right? Now, the good news is that depending upon the electronic environment in that region, in the next door neighbor region, like whoever is your next door neighbor, if it is a halogen, if it is an oxygen, if there is a carbonyl group, if there is an electron pushing group, like oxygen but connected in a slightly different way, something with a lone pair that can be donated and electron density can be pushed into you. Okay, things like that. There are so many factors that can affect the electronic environment. Apparently, the electronic shell, electronic cloud can be thinned out or thickened, okay, which is hard to explain, but apparently the subtle effect that the electronic environment can have on my, if I'm a nucleus, around me on my electronic cloud is significant enough to be measured by the spectrometers built by human beings. Okay, so sometimes the electronic shield could be thick. Sometimes it could be a pretty thick one. Okay, sometimes sometimes the electronic shield could be pretty thin. So these are the two extreme cases. Okay, this is thick and this is thin. And you need to really be able to connect the dots here. Okay, so imagine this extreme scenario versus this extreme scenario. Let's get a few concepts straight at this point. I'm going to ask you guys some questions and you guys need to participate so that you understand it very well. Let's say the hydrogen that's here, and the hydrogen that's here, which has thin shield. This guy has thick shield. Okay, and B0 is an external magnet. Okay, B0, which is the external magnet. External magnet. This is B0. Okay, let's connect the dots first. Thick shield, thick electronic shield cloud versus thin electronic cloud. Connect the dots. Electron withdrawing groups in the neighborhood, electron withdrawing groups, and electron donating groups. Two extreme scenarios. You have one hydrogen here and one hydrogen here, and one of them is surrounded by electron withdrawing groups, and one of them is surrounded by electron pushing groups, donating groups. Which one is which? Which hydrogen, with the thick cloud or the thin cloud? Let's deal with one thing at a time. Which of them is in electron withdrawing environment? Up or down, thick or thin? Electron withdrawing environment.
Thin.
Top or bottom, thick or thin?
Bottom, I'm thinking we in more.
Hannah, can you tell me? Okay, so we have one hydrogen is in electron withdrawing environment. Is it this guy with a thin shield or thick shield? You answer thick or thin. One of the two words.
Thin.
Okay, one answer is thin. Anybody else wants to chime in?
Thick.
Electron withdrawing environment. Thin or thick?
Thick.
Juliana, you think it's thick?
Yes.
Okay, anybody else?
I think it's a top one as well.
You think it's top one? So let's say, let's use an example. I wish we had a bigger board. Let's use this scenario. Carbon, carbon. Let's say I'm going to color the hydrogens. Okay, let's make okay. Let's make one hydrogen red and let's make one hydrogen purple. Okay, and let's say this hydrogen is next to I'm also trying to either teach you guys or remind you guys about electron withdrawing groups versus electron donating groups. Okay, let's say what else shall I put here? Let's just keep a hydrogen, maybe two hydrogens here and two hydrogens here. They're equivalent, and I'm going to stick a fluorine here. Okay, now these two are one kind of hydrogen and these two are another kind of hydrogen. We talk about equivalency, equivalent hydrogen. So a molecule can have like 10,000 hydrogens, but there could be only 5,000 types of hydrogens or 400 types of hydrogens. Altogether, this molecule has 3 types of hydrogens. One type, second type, and third type. Let's ignore it for the first time. Let's not focus on these hydrogens. Let's focus on the red and the purple. Let's ignore these guys. Okay. If you look at the methyl group, you guys remember the electronegativities, electronegativity property, electronegativity of hydrogen versus carbon. Who remembers? What's the electronegativity number for hydrogen and what's the electronegativity number for carbon? Who remembers? What's that for hydrogen? Come on.
1.5.
No. Don't manufacture numbers. It's 2 point something and 2 point something for both. Which one is low? Which one is high? What's the number for carbon? What's the number for hydrogen? Anybody? You guys have all
Isn't it like hydrogen's like 2.2, carbon's like 2.5, I think?
Carbon is 2.5, hydrogen is 2.1 or 2.2. I'm more used to 2.1. Yeah, it doesn't matter. Okay, if hydrogen is 2.1, thank you, Eshan. If hydrogen is 2.1 and carbon is 2.5, which way will the electron, the bonding electrons be kind of polarized toward? Will they be pulled toward carbon or will they be pulled away from carbon toward hydrogen? Which way would they be pulled? Imagine that they're like, go ahead.
I feel like they're going to be pulled towards carbons because carbons is more like electronegative, has a higher
Yeah,
electronegativity,
okay.
so it's going to go more
Sounds
towards the
good.
carbon.
Yes, perfect. Okay. So if it's kind of like I'm walking with 3 little triplets and they're my, maybe I can't say they're my children anymore, too old. Let's say they're my grandchildren and I'm standing in a line and they're pushing me. And so I end up pushing the poor guy or lady who is standing in front of me. So let's say I'm trying to return something to Amazon in UPS and they're pushing me, they're just messing with me and I end up pushing the next person. So this effect can be felt up here. So an alkyl group is electron donating by inductive effect. This effect is called inductive effect, which arises due to the difference in electronegativity. Okay, inductive effect is a temporary effect. It's not like resonance effect. Hopefully, you guys have learned all this stuff in 128A. Okay? So this is an electron donating group. Compared to that, over here for the purple hydrogens, the carbon is 2.5 electronegativity. What's the electronegativity number for fluorine? Who remembers? What's that number for fluorine?
It's ridiculously high, essentially, but it's like 3.9 something or 4.
Yeah, let's say 4. Thank you. Okay, so if it is 4, then it's pulling electron density like crazy toward fluorine, okay, away from this side. So between the red hydrogens and the purple hydrogens, which hydrogens should have thinner cloud around their nucleus? These guys or those guys? Which one, red or purple, should have thinner electronic cloud or shield around their nucleus? That or that? You can say left or right, or you can say red or purple, if you can see the color.
Purple.
What did you say, Sebastian?
Purple.
Okay, so Sebastian thinks that these guys should have thinner cloud. Juliana, what do you think?
I agree.
You agree? So when you have electron withdrawing groups, basically what kind of friends will make your bank balance thinner? Those who are takers or those who are givers? It's that simple. The takers, when you hang out with your takers, you will realize that, oh my God, my dad sent me like $800, but in 2 weeks, I'm down to like $50. What's going on? Because you are surrounded by freeloaders and self-centered people who are basically takers. Okay, but if you're surrounded by nice people who like to share, maybe your bank balance will be around the same place, or maybe a little more, because they're helping you save money, right? So electron donating groups will make the cloud thicker, and electron withdrawing groups will make the cloud thinner. Okay, so now, so thick cloud and thin cloud, okay? So this is connected with electron donating groups. I'm going to write it more cleanly a little bit later. And thin cloud is connected with electron withdrawing. I'm doing a pretty bad job, forgive me, but I'll clean up and put everything together in a nice way soon, before we break for today. Okay, so thin cloud, electron withdrawing groups, thick cloud, electron donating groups. Now you tell me another, let's connect 2 more dots. We connected 2 dots, thick cloud versus thin cloud, and we connected electron donating groups and electron withdrawing groups. Which nucleus, this guy or this guy, the external magnetic field is constant, okay? External magnetic field is like sun. Sun is constant, okay? But let's say there are 2 planets, planet 1 and planet 2. One planet has, and both have the same kind of humans walking around on the surface. One planet has thicker cloud, one planet has thinner cloud. Which magnet will be a stronger magnet, up here or down here? Which magnet will be a stronger magnet, will be a more powerful magnet? Up or down?
The bottom one?
I'm hearing you. I'm trying to keep a straight face so that I'm not sending you a message, Jasmine. The bottom one, Jasmine thinks that this is the magnet that's going to be a stronger magnet. Anybody else wants to chime in? What do you guys think?
I think she's right.
She's right, Sebastian. Anybody else? Couple more people, maybe?
I would think she's right because of as like the fluorine's highly like electronegative. So
Don't
it's
think
gonna be-
about fluorine. Don't think about fluorine. Just think about one magnet surrounded by a thin cloud, one magnet surrounded by thick cloud. And you have the same strength external magnet, same sun, two planets, one with thick cloud, one with thin cloud. In which planet the human will be feeling the heat more and be more agitated or more energetic? With the thick cloud planet or thin cloud planet?
Thin.
No will be the thick cloud if they're more agitated because they're more likely to donate their electrons.
When do you get depressed? When it's a cloudy day or when it's a sunny day? When are you more energetic? When do you feel sun's rays more? When you have a thin cloud or no cloud, or versus a very rainy day with super thick cloud? Which days you feel the sun more? Which days you absorb more sun's energy, sunshine? Just keep it simple, Hannah.
Yeah, no clouds, so thin.
No clouds are thin. Hannah, I mean, is anyone else having some? This is very legitimate confusion because you're learning quite a few, like trying to connect a bunch of different dots today. So this confusion is very legitimate. And the confusion may come later on. You might think that, oh, I'm getting it now. But tomorrow morning or when you're falling asleep, if you're thinking, you might get confused. And this is very expected and very normal, okay? Thick cloud, electron donating groups. Thin cloud, electron withdrawing groups. We get that done, check it off. Next connection, next dot to connect. Which one is stronger magnet? The one that is surrounded by, imagine, Hannah, that the magnet is getting energy from that external magnet. Okay? The central nuclear magnet is getting its power source from here, from the sun. Okay? Unfortunately, the one that's surrounded by electron donating groups has a thicker shield. The sun's power, sun cannot shine through the thick cloud as much as it can shine through the thin cloud. Can you see that happening? So this guy is going to be more energetic. This guy is going to be a stronger magnet. I'm going to pause for 15 seconds and let you guys kind of ponder.
Okay, so I think if you say magnetism, you think of like magnetic fields, more electrons, more energetic electrons equals a stronger.
It's induction, right? It's induction. If the way the bar magnet is going to move around on surface of the planet Earth is going to be different than on Moon, right? Because Earth's magnet is stronger than Moon's magnet, right? So this guy is going to be a stronger magnet if I have a bar magnet hanging from my ceiling. It's going to be stronger on Earth and stronger on Moon. But this guy is probably going to be, if sun was powering like solar cells. Imagine the solar cells. The solar cells are producing more energy on a sunny day or on a cloudy day. Which days? When there is
On a sunny day?
On a sunny day, because it can get more energy from the sun. So similarly, the external magnet, which is inducing the magnetic behavior in the nuclear magnet, which is helping it line up with itself, that induction is going to be working more strongly when the surrounding shield is thinner. We can discuss further during office hours. If anybody has any questions, we can meet. Let's keep moving. Okay. So thin cloud, that magnet is stronger. So I'm going to connect another dot. So thin cloud, stronger magnet. Thick cloud, weaker magnet. Okay, that means the value of delta E the value of delta E is less for that guy than this guy. That's why NMR works. If this were not true, or if this were not measurable, or this were measurable and true, but then we could not make sense out of it because the resolution would be so screwed up that you wouldn't be able to tell the difference, then nothing would exist. We wouldn't be talking about NMR spectroscopy right now. Many such techniques have probably not been able to be developed because it's still not being possible by humans to exploit it, right? So the connections are thick cloud, donating groups, thin cloud, withdrawing groups, thin cloud, strong magnet, thick cloud, weak magnet. Weak magnet, smaller value of delta E. Bigger value of delta E means thin cloud. Okay, I'm going to write this down separately and it's going to be less cluttered. I think it'll probably make more sense to you guys. So let me just take a snapshot of the board and then let's go from there. Yeah, I don't want to spend like another 3 days on NMR because that has been my trend in the past. Let me erase the board. I'm not going to ask you to look at the board anymore. Let's keep things simple. I'm going to redraw this thick cloud and thin cloud, but then I'll try to like make a little more sense out of it by just with an uncluttered board and just the key points. I'm going to just write down the key points so that it's easier for you to fathom and kind of like put things down in your mental compartments. Okay, so all right. One magnet, a nuclear magnet, thick cloud. That's the electronic cloud. That's black is the nucleus, red is the electronic cloud. This is thick. Okay. And down here, nucleus in the middle, and you have, let's say, thin electronic cloud. Okay, let's connect the dots. I'm going to use different color coding. Okay, this is, I'm just going to write down what it is. Thick electronic. I'm just going to use that colloquial word, cloud. Let's call it cloud. Thick electronic cloud, thin electronic cloud. Okay, that's bullet point. I mean, that's dot number 1. That goes with electron donating groups. Electron donating groups in the vicinity. Okay. Now for this guy is electron withdrawing groups. In the vicinity. If you still have questions, feel free to set up an office hours with me. I will be more than happy to go over it one more time. Pick 10, pick 10, the same thing. Electron donating groups, electron withdrawing groups. Strength of the magnet. Stronger nuclear magnet weaker nuclear magnet. Okay, what else? Delta E, delta B minus, E beta minus E alpha against minus with B0, that those two values, the relaxation energy. Okay, this means smaller delta E. This one is greater delta E. Just make sure, browse through them, scan the boxes and make sure that it makes sense.
Wasn't the magnet for thin supposed to be stronger?
Say that again.
Wasn't the magnet for thin supposed to be stronger?
Yes. Sorry. Thank you. Thank you for catching that. Yeah, I just solved it. Weaker nuclear magnet, stronger. Thank you so much. This is Andres. Thank you, Andres. Okay, yeah, sorry. Take a look. Make sure that I haven't made any other mistake. Donating, withdrawing, weaker, stronger, smaller, greater. Yeah, sounds good. Okay, so because of this phenomenon, it works for us to distinguish between different hydrogens. So if there is a molecule that has 10 different hydrogens, you're most likely be able to find out that all the peaks that are measuring the delta E for the 10 different protons, 10 different hydrogens, you can see the 10 different absorptions or 10 different relaxation energy measurements, and they are different. You know, the precision and the accuracy and the signal to noise ratio is good enough for you to be able to distinguish between them. And you can tell what's going on there. Okay, so that's very important. Are we good so far? Okay, so this is very important. Why is this important? This helps us because helps us distinguish between different, I'm just going to say nuclei, whether it's hydrogen nuclei or some other elements nuclei, it doesn't matter, different nuclei. In this case, of course, we are talking about hydrogen. 1H means it's proton, it's hydrogen, like normal hydrogen nucleus. So this is a big deal. This is a big deal because if this were not true, this whole thing wouldn't work out. Okay. So what I'm going to do is I'm going to take a snapshot and keep moving on to the next concept. There are a few other concepts, so that's pretty critical. So we have to learn that. I'm going to give you 15 more seconds, and if you think that this is under control, then I'm going to just erase it. There's not much going on here. Just one little bit of concept. one small concept that's being captured on the board. Okay, are we good? Feeling confident? Okay. So I'm going to try to tell you like what other factors can affect delta E, okay? The energy. I'm going to raise last call. Thick, donating groups, weaker magnet, smaller delta E. Thin, electron withdrawing groups, stronger magnet, larger value of delta E. And this is a big deal because if this didn't happen or couldn't be measured or couldn't be interpreted, then what's the point? I mean, all of these darn hydrogens would show up at the same place, right? No use. It would have been completely useless, this whole technology. So I bet at the very beginning when people were trying to figure out NMR spectroscopy, they had a hard time, and eventually they could crack the code, and which is great. I really do not know the history of it much. Again, I had learned it at some point in graduate school, but it has faded. The knowledge has faded, like faded glory, faded knowledge. Okay. So delta E, before we get to the equation, so I just want to make sure that you understand what that is. So E beta minus E alpha. Okay, remember E alpha is less with B0 when the the nuclear magnets are lined up with B0. E beta is against B0 when the radio frequency has been applied and the magnets have been forced to turn around against B0. High energy minus low energy, right? So you need to just keep that in mind. And this is delta E. Okay, what are the different parameters that can affect delta E? Of course, number one, the first thing that can affect delta E thickness of electron cloud. In other words, electronic environment. Clear? That's clear, right? Think about it for like 10 seconds. That's a bad line. Yeah. You follow that, you follow that, you follow that. That's something that we've been talking about for quite some time. And it's affected by that business, electronic environment. Electron withdrawing groups, electron donating groups. You need to really put things in perspective and not lose the real meaning of it. Number two, what else can affect it? What do you think about the strength of the magnet? If B0 is a more expensive, really powerful magnet versus B0 is a really weak 1960s 60 megahertz magnet, do you think that B0, if we had a more powerful sun, would you feel the heat more? So should B0 affect the external magnetic field, affect delta E? External magnetic field, which is B0. Do you think that should affect it? What do you guys think? Stronger external magnetic field means greater delta E. Weaker external magnetic field means lesser delta E. Do you think this arrow it makes sense? It's not a trick question. Just answer the way your gut feeling is at this point. Stronger magnet, stronger sun versus weaker sun. If the sun's power changes, it's changing every day, right? There is a small amount of change. Probably tomorrow morning, the sun will be slightly weaker. So will you feel a little less energetic? Theoretically, I know that it's not measurable, but do you think that during your time of your life on Earth, on Mother Earth, on planet Earth, by the time you're like another 20 years have passed, do you think that the sun will become weaker and that will affect you accordingly? I mean, even though it's not measurable? Do you think this is true? External magnetic field will make delta E bigger or smaller depending upon the strength of it? What do you guys think?
I think it will affect it.
Anybody else? Affected or not affected? Yes or no?
I think
Affect? Yeah, okay, so that's true. So the thickness of the electronic cloud can also be measured in some kind of magnetic field, because when you have a magnetic electronic cloud, it also generates a local magnetic field, and that's often called the shielding. Okay, it's like that shield that the Death Star had developed, okay, before it could be attacked. Okay, so this is B0, and this is often called BS. Don't laugh. BS. B shield. That's a local magnetic field generated by the cloud. Thicker cloud, greater BS. Thinner cloud, lesser BS. Got it? Make sense? Okay. What do you think about the intrinsic property of the nucleus? I mean, between a human, a dog, and an elephant, there are three types of elements like hydrogen, carbon, and phosphorus. Do you think that some of them by birth, by their intrinsic property, will be a stronger magnet than the other guy? Do you think that's true? Or all different elements, whoever can have this nuclear magnetic property, should be the same strength magnet? Do you think that will vary from element to element? What's your gut feeling? Again, this is not a trick question. Answer the way follow your heart. What do you think?
I think
Different- Go ahead.
I think it'll vary between element. I think elements are not very consistent.
Okay. Anybody else? Hannah, thank you. Anybody else? I'm not saying yes or no. What do you guys think? Different elements should have different strengths of magnetic field in their nuclear magnetic property. Somebody else?
they have different strengths due to the differing amount of protons.
Yeah, exactly. Thank you. It's pretty good answer. So yeah, so the intrinsic property, what color shall I use? Let's use blue. Let's use purple. Okay. How should I say it? I'm just going to spell it out in like colloquial street language, not necessarily street language, depends on which street you live on. Different elements will, or not will, exhibit different nuclear magnetic property. Okay. This is usually denoted as gamma, and I'm kind of like, I'm not going to use that R word. I have some disability. I cannot distinguish between, I cannot write gamma and nu differently. So my gammas look like nu, but you know this is gamma. I'm going to say that it's gamma. This is gamma. You can make fun of me if you want. So gamma is the intrinsic property of an element for their nuclear magnetic property, okay? And it's called gyromagnetic ratio. GYRO magnetic ratio. Okay, gyromagnetic ratio is gamma. Okay, and that's just the property. Just by birth, a proton, a hydrogen nucleus is about 4 times as strong as a C13 nucleus. I'm just going to write that down. The gamma of hydrogen is about 4 times gamma of C13. Okay, so by birth, hydrogens produce better signals to noise ratio. Okay, carbon-12 doesn't work. They don't have that nuclear magnetic property because they have even number of protons. It has to have odd number of protons and or neutrons. Okay, so 1H works, C13 works, but the gamma of the gyromagnetic ratio of a hydrogen nucleus is by birth 4 times as strong as that of the carbon. Okay, that's another thing. What else am I missing here? Okay, so that also affects delta E. Okay, what else affects delta E? I think that's pretty much it. Gyromagnetic ratio will affect delta E. Gamma will affect delta E. Gyromagnetic ratio is gamma. B0 and BS will affect delta E. And let me just connect B0 and BS. Okay, it's important. Okay. The third term, there is one that's like external magnetic field. You are given the sun is out there, that's B0. This is the sun. Okay. This is B0. It's out there. BS is the cloud. Okay. Here is the sun. Here is planet Earth. And here is the cloud. That's BS. And this is B0. Okay. And the sun's rays are trying to come in and penetrate through here. This is Earth, Mother Earth. Okay. And the nucleus are here. Okay. So B0 is getting deducted. Whatever BS is there, whatever the thickness of the cloud is, whatever the magnetic property of the cloud is, that's kind of getting eliminated from B0. If there was no cloud, then I would feel exactly how much sun's rays are. Okay. So there is a third term that's called B effective. B effective is what I actually feel on the surface of Earth. That's BE. Okay, so let's introduce that. BE is effective field, effective magnetic field. Or whatever the strength is. BE is equal to B0 minus BS. Make sense, you guys? Sun, cloud, what you feel on the surface of Earth. That's the whole energy minus the shielding, and whatever comes to the shield, you feel it. Make sense? Does it make sense to you guys? Say yes or no.
Yes.
Thank you. So now there is an equation. I'm not going to get into the details. I haven't got to the PowerPoint yet. So delta E, you know that it's H multiplied by nu. Planck's constant multiplied by nu. My nu looks like gamma. That's nu and that's gamma. They're different, okay? Equal to H remains constant. H is up here. Let's just keep it simple. H multiplied by gamma. This is gamma, not nu. Multiplied by B effective divided by 2 pi, something like that. Yeah. The book sometimes puts B0 here, but since I already explained it to you, I didn't want to do it the wrong way. It's not B0, it's B effective, because that's exactly how the nucleus feels. The nucleus doesn't feel entire B0, it feels sun minus cloud. That's what I feel on the surface of Earth, okay? That's actually BE. You can also write it slightly differently. You can say it's Planck's constant multiplied by gyromagnetic ratio gamma multiplied by B0 minus BS. B0 minus BS divided by 2 pi. Okay, so you can see that B0 is greater, delta E is greater. Gamma is greater, delta E is greater. If B0 goes up, if the strength of your magnet is higher, more expensive, more money, you have more cash, UC Berkeley versus UC Irvine versus UC Davis versus CSU Fresno versus City College, as the funding goes down, you have a weaker magnet because you couldn't afford it, right? So B0 is less means delta E is less. BS is less means delta E is more, right? So the cloud, if the cloud is thicker, delta E is less. If cloud is thinner, delta E is more. If B0, the strength of the magnet is more, then delta E is bigger, better signal, maybe more signal to noise ratio. B0 is less, delta E value is less, and it goes accordingly. For hydrogen, you are in an advantageous position because gamma for hydrogen is 4 times that gamma for C13, carbon 13. Okay, unfortunately or fortunately, whatever. So carbon 13 is always a pain because you need more sample to get similar signal to the noise ratio. Okay, so take a look at it. We'll take a look at the time situation and 4:44. Well, time situation is not looking that good. I think we're going to stop here, and we'll go from here on coming Tuesday. Have a good weekend, guys. I'll read all the emails. I'll take a look at the submissions, check the times and everything else. I'll start grading probably from tomorrow. I'm still a little under the weather from that second Moderna vaccine. So hopefully if I feel good, maybe I'll start pondering. I'll start fiddling with the submitted exams on Canvas, and then we'll go from there, okay? I'll probably have a better answer to talk about. Office hours are still there. If I ignored it or if I didn't respond to your queries, my bad. I've been a little distracted and not feeling too well, but I promise that I'll have office hours from coming week. And for before the final, I would like to have a review session with you guys. Okay, we kind of go over stuff, and yeah, basically we can work out the quizzes and the exams that we have had so far. Okay. So I'm going to switch to the front camera and then see if anybody else has any questions or queries. You guys have a fantastic weekend. Anything else?
How did did your wife have the vaccine shot?
Yeah, she was in worse shape. She ran like 102.7. It's basically a sign that your antibodies are being produced. But it's not a big deal. You know, I ran a little fever. I have very high pain tolerance. Sometimes I bump into the wall or I don't know, beds, and my leg will be bleeding and I will not even know. Somebody else will say, Shantanu, what's that? Like, okay, I'm bleeding. Yeah, so I hurt myself. Yeah, I have very little pain tolerance. I have very high pain tolerance. I'm not bragging. I mean, that's the way it is. Sometimes I worry, like, I hope my pain receptors are still working. Yeah. So, yeah, so I don't know how much, what was my fever? I didn't even bother to check. 100 point something, 101 millimax, but Kalyani ran like 102.7. He was in pretty bad shape. But this is Moderna. I'm hearing again. I do not know if there is a statistical significance to it, but that women are being affected a little bit more than men. That could be some truth to it. I'm not sure. I'm also hearing that maybe Moderna's second vaccine is a little more effective than Pfizer, or doing this business. You know, I don't know. I don't want to say something really inappropriate or start like a what is that called, conspiracy theory, but then I trust Moderna a little more than Pfizer because I have seen Pfizer doing sketchy things in the past, in the last 20 years. I trust Pfizer a little bit less because as much as they may be a huge company, I don't know if you have read, Moderna scientist who invented Moderna, that mRNA strand, she was ignored for a long time. She didn't get any grants. She didn't get any support. People ridiculed her, made fun of her. She was almost, I think she might have lost her job. But so I have much more sympathy because I think it's more sincere. But Pfizer's vaccine is probably fine. I don't think there's anything wrong with it, but some of the numbers are a little funny. If you remember, I do not know how many of you follow it, but when Pfizer's vaccine first came out, their efficacy was 90%. Then Moderna came out with 95% efficacy. Within a week, Pfizer came out with a press conference saying that their vaccine is 95.5% efficacious. I don't know if this is all true. Again, I'm not trying to spread rumors. I'm not trying to start a conspiracy theory, but my wife had undergone a neck surgery. She had slipped disc in her here in the cerebral over here between C5 and C6. In 2002, right before we went back to India, she had a huge neck surgery. She was taking this painkiller, which affects the synthesis of some pro-inflammatory agents. It's called COX-2 inhibitor. I forget the name of the drug, Pfizer's drug, and she actually liked that drug very much. She said, "Oh, it makes me feel so good. I don't feel my pain anymore." It was almost funny. We were all teasing her. It turned out that Pfizer had lied about some of the side effects, cardiovascular side effects. They had to pull it back. There was a lawsuit. They basically withdrew that medication. And companies do that. The corporate world is vicious. I mean, talking about moral values and ethical values, it goes through the ionosphere, man. When there's a shark eating sharks and shark eating fish. It's a vicious environment. So I personally have a little soft corner for Moderna, but that doesn't mean anything. Yeah, someone is making jokes. Sean. No way. Yeah. I actually, I don't know if you guys remember, I worked in pharmaceutical industry for like 8.5 years. and I had enough up to my neck, and I basically ran with my tail in between my legs to Fresno State. Thanks to Fresno State for giving me a job. Anyway, you don't have to hear that story. You guys are doing okay? Saeed, Roxana, Alexia, Sean, Jocelyn, Sebastian, Dane, Juliana, Dolly.
I only asked because my parents had the first round of shots.
Which one?
Moderna.
Yeah, well, second round of shots, just make sure they're not too busy or they're not traveling. Yeah.
Okay.
Yeah, some people didn't have much. There is also another theory that when you have more reactions, that means you are not exposed to the COVID-19 virus. So if you are having a lot of reactions, that means the antibodies are being generated for the first time. If you haven't had much reactions to the second shot, that means you may have already generated the antibodies from your exposure to COVID-19. So whether you knew it or not, you might have had COVID-19 exposure. Again, this is, I mean, it's not a conspiracy theory, but there could be some truth to it, or there may not be any truth to it. I do not know. Because I think each individual will react differently too, depending upon your bodily makeup. You know, some of us, when we have fevers, you know, everybody reacts differently. Some people freak out. Some people don't freak out, like, you know, as if like nothing has happened. So there could be so many factors. We'll probably learn more as days go by. Yeah, ask your parents not to be involved with too much responsible work or, you know, any commitments. Just take it easy after this vaccine. The ordeal may last up to like 3 days, if there is an ordeal.
Okay. Thank you.
Anybody else? Any other random discussion?
Well, going on what you said, my family and I, we all had COVID-19, and my mom just took the first round of the Pfizer shot as well, and she didn't have any side effects.
Usually the first shot is not doing anything. Let me know how the second shot goes, Justin.
Okay, thank you.
Yeah, no problem. The second shot might be different because I think the first shot is just kind of like you know, it produces the antibody, and the second shot kind of brings it to a shock. I think that the body reacts more vigorously to that. Yeah, I'll be curious to know how the second shot goes for your parents, Justin.
Okay, thank you. Have a good day.
Yeah, bye. Bye, Sebastian. Bye, Justin. Take care.